Hi everyone, I'm Santhi from Department of Mathematics and Statistics, Bhavans Vivekananda College. I'm here with my lesson 13 of linear algebra on vector spaces. In this lesson 13, I'm going to explain the following few concepts. First one, spanning set of a subspace, and next one, spanning set theorem, and the third one, finding a basis for a subspace from a given spanning set using spanning set theorem. Let us see what is spanning set of a subspace. Let V be a vector space and H is a subspace of V. Then a set S is equal to set containing V1, V2, V3 and so on Vp, some p number of vectors in V, the vector space V, such that H is equal to span of S. That means the subspace H is spanned by S. That is span of set containing V1, V2, V3 and so on Vp, these vectors. Then S is said to be a spanning set of the subspace H. So what do you mean by that? Any set of vectors in V, if it is spanning the subspace H, that means every vector of H can be written as a linear combination of these vectors, then you call this set as spanning set for the subspace H. Here we are with spanning set theorem. Before this we had a definition of spanning set. Now we are going to have a theorem related to spanning set. So here the statement, let S is equal to set containing V1, V2, V3 and so on Vp be a set of vectors in V and H be a subspace of V such that H is equal to span of set containing V1, V2, V3 and so on Vp. What do you mean by that? This S is a spanning set for the subspace H. Now, first bit is, if one of the vector in S, let it be Vk, is a linear combination of the remaining vectors in S. That means here you have p vectors. Among these vectors, suppose any one of the vector, it can be any vector v1 or v2, v3, any vector which is a linear combination of other vectors. Then the set formed by removing Vk from S still spans H. That means if I find any vector among these which is a linear combination of other vectors, then I can remove that vector. Then all the remaining vectors after removing that, still they span H. That means still the remaining set will be a spanning set for the subspace. This is the first bit. Second one is, if H is not equal to set containing 0, that means H has vectors other than 0 vectors, not just a 0 vector. Because if H has only 0 vector, then there is nothing to do because it is a 0 space. There is no meaning for basis for this. So if H is not equal to set containing 0, then that means if it has some non-zero vectors, then there is some subset of S which is a basis of H. That means if you take a non-zero subspace and you have proved already A, that is it has a spanning set, then there will exist a basis which is a subset of this one. That means from this spanning set you can obtain a basis for H. That is what spanning set theorem states. Let us go through the proof. So here it is given S is equal to set containing V1, V2, V3 and so on Vp be a set in V such that subspace H is equal to span of V1, V2, V3 and so on Vp. So this is given to us. What do you mean by H is span of this? Any vector in H can be written as a linear combination of these P vectors. So I'm taking here implies X belong to H. Taking a vector X from H implies there exist scalars C1, C2, C3 and so on Ck minus 1 such that x is equal to c1 v1 plus c2 v2 plus and so on plus ck minus 1 vk minus 1 plus ck vk plus ck plus 1 vk plus 1 plus and so on cp vp. That means this x can be written as a linear combination of all these vectors. That is what we have written. How do we write linear combination? How many vectors are there? We will take those many scalars. With those, we'll write the linear combination. This is our equation 1. Now, let us try to prove the A bit, first bit. In the first bit, what we have, suppose if there is a vector vk, which is a linear combination of other vectors. So, I am taking that, let vk be a linear combination of vectors v1, v2 and so on vk minus 1. Its preceding vectors I am taking here. That implies there exist scalars a1, a2 and so on ak minus 1 such that this vk is equal to a1 v1 plus a2 v2 plus and so on ak minus 1 vk minus 1. That is vk is a linear combination of these vectors. This is equation 2. Now let me substitute equation 2 in equation 1. In equation 1 you have this vk here. So in this place of vk, from equation 2 we have vk value as this one. So let us substitute this. Substituting 2 in 1, I'll get x is equal to c1 v1, that is c2 v2 plus and so on ck minus 1 vk minus 1. Till here it's fine. Then ck into in place of vk, ck into in place of vk, I am writing this entire equation 2. That is a1 v1 plus a2 v2 plus and so on ak minus 1 vk minus 1. Vk value I substituted here. Then rest of the terms are the same. Plus ck plus 1, vk plus 1 plus and so on plus cp vp. Now let us simplify this. I have here v1 term, I have here also v1 term. Similarly v2 term, 1 term is here and v2 1 term is here and so on. So let me simplify, regroup the terms, get all v1 terms. So if I take v1 common, I will get c1 here and then here ck into a1. So we'll write c1 plus ck into a1 into v1. Then let us group v2 terms. Here there is one v2 term and here there is another v2 term. So c2 plus, this is coefficient here. Here the coefficient is ck into a2. ck into a2 into v2. Like this plus and so on. Up to where we can take common, I have up to ck ak minus 1 vk minus 1. Here also I have vk minus 1 term. So let me take vk minus 1 common. Then what do I get here? Ck minus 1 and here I have ck into ek minus 1. So ck into ak minus 1 into vk minus 1. Then the remaining are the same, plus and so on, plus remaining, these are all the same. Only the change is here we don't have the term vk. In place of vk we substituted these terms and we rearranged it. So what happened here in this equation, there is no vk term. v1 term is there, v2 term is there, vk minus 1 is there. Next we have vk plus 1 term only. We don't have vk term. So it is equal to a linear combination of v1, v2, v3 and so on, vk minus 1, vk plus 1 and so on vp. So vk is missing. But still after removing that also, you are able to write x as a linear combination of v1, v2, v3 and so on, vp except vk, deleting vk. What do you mean by that? After deleting vk from the set, still every vector in x can be a linear combination of the remaining vectors. That means H is still spanned by this set. What is this set? It is little different from this. That is, here vk is removed. After removing vk, the remaining set is also still spanning H. That is, it is a set formed by removing vk from S and it is still spanning H. This is what the first bit. Now comes the second bit, that is let H is not equal to set containing 0. What do we mean by this? H is not just having only 0 vector. H is having even some more vectors other than 0 vector. That is what we mean by any set which is not just a set containing 0 vector. So H has some other non-zero vectors also. Now we need to find some subset of S which is basis for H. Now we have S, that is a spanning set here. Now we are in search of basis for H. What is basis? Which is a linearly independent set and spanning H. So this S is already spanning H. Only the thing, if it is so, our first argument is if S is Li, then S itself forms a basis. Because already it is given that H is equal to span of S. But there is no guarantee that S should be always Li. So if S is not Li, that is otherwise, that is if S is not Li, then it is LD. So if S is not Li, then it is LD. Now, what do we know about LD set, linearly dependent set? We had one theorem, an important result on a linearly dependent set, that is here implies there exists some vector Vk, k greater than 1. That means that Vk should be from V2, V3 and so on. It cannot be V1. Vk, which is a linear combination of its preceding vectors. So this is a result on LD set. So now we are supposing if S is LD, then this result should be true. That means there will be a vector Vk in S which is a linear combination of its preceding vectors. Then what do? We'll remove that Vk from S and form a new set. That is S1. What is S1 for us now? It has all the vectors of S except Vk. We remove that Vk from this. Then we claim that S1 still spans H. That is by AY. In A we proved that if from a spanning set, if you remove a vector which is a linear combination of other vectors, still the set with the remaining vectors must span H. So we removed Vk. So the remaining set, that is S1, must span H. Right. Now let us see what will be S1. Will it be Li or LD? If S1 is Li, then what happens? S1 itself forms a basis for H. Then if S1 is not Li, then again. Otherwise, if S1 is not Li, then it is LD. That implies if again LD set, what is that property we used on LD set? There will be a vector in that set which is a linear combination of preceding vectors. The same argument if we apply on S1, if it is LD, then there exists some vector Vj in S1 which is a linear combination of its preceding vectors. Now what do? Again the same way how we removed Vk from S, here let us remove Vj from S and form a new set S2. So again what happens? We removed a vector which is a linear combination of some other vectors, hence this S2 will still span H. So what are we doing from the spanning set? We are going on removing those vectors which are linear combinations of preceding vectors or other vectors. But still after removing also all these sets are spanning H. That is what we proved in A. Then as we continue the same above process of removing a vector which is a linear combination of its previous vectors from H. So we'll continue the same procedure like this, removing a vector which is a linear combination of other vectors, its preceding or previous vectors. Then what happens? How long can we remove? How many vectors can we remove? What is S? It is a finite set. It has p number of vectors. If it has p number of vectors, after a finite number of steps, we must obtain a subset of S, which is Li, and hence forms a basis of our H. Why? Because if it is not Li, what do? We'll continue removing. But how many we can remove? S has only p number of vectors. For example, let me say this S has some 100 vectors. Then I go on remove one by one vector. At some step I claim that then there must be a set which is Li and spans, and hence it forms a basis. Suppose at 50, I removed 50 elements out of 100, then I got a set which is Li, then it forms a basis. Okay, then fine, not 50. I removed 60 vectors, I got a Li set. Otherwise, the worst case what happens, out of 100 vectors, I removed all 99 vectors. Still I couldn't find, like up to 98, I couldn't find any Li set. After removing 99 vectors, then how many will be remaining in S? Only one vector will be in S maximum. Then only one vector in any set which is a non-zero vector, it must be linearly independent. So at the last, after removing all vectors except one vector, you must obtain an Li set. So, and hence that forms a basis. So that is what we stated here. At the most, we may remain with a subset of one non-zero vector in S. Like I explained you, out of 100 vectors, if you can't find after 50, after 55, after 60, after 65, but after 99, only one vector is remaining, a subset of one non-zero vector in S, then that must be Li. You need not prove anything. Then it forms a basis for H. That means at any cost from the given spanning set, by removing such vectors which are linear combination of preceding vectors, at least, not at least, at the most, at the last step, you must obtain an Li set which spans H, and hence that forms a basis for H. This proves the theorem. Now, keeping this theorem, the theorem what we proved before, in view, let us see a procedure to find a basis for the space or subspace spanned by a given vectors. So, suppose you are given, consider a set S is equal to set containing V1, V2 and so on Vp, such that a vector space or its a subspace H is equal to span of S. That is, S is spanning set for H. Now our task is to find a basis for H using the spanning set, not from any other set, from the spanning set. Then we will use the concept of spanning set theorem. For that, here what we do is, we'll take a matrix A is equal to, what will be columns in this matrix? Whatever the vectors are there in S, V1, V2 and so on Vp, they will be columns in this matrix A. So this is a matrix with given vectors as columns. Then next step, reduce A to echelon form and mark the pivot columns. So we know how to reduce to echelon form and mark the pivot columns. Then what happens? If you mark the pivot columns, you may have some columns as pivot columns, some columns not pivot columns. So a column which is not a pivot column means, it means that that column represents a vector which is a linear combination of other vectors, right? So a column which is a pivot column means it is an independent column. It is not a combination of any other vector. But a column which is not a pivot column, it is a linear combination of other vectors, other columns. So here our next step is, the columns in A that are pivot columns in its echelon form will form a basis for H. That is, for example, I reduced echelon form to A to echelon form, and then it has some like 5 columns suppose, and among those I got C1, C3, C5 as pivot columns. That means C2 and C4 are linear combination of other vectors, other columns. So I removing C2 and C4, a pivot column C1, C3, C5 in echelon form, then their corresponding vectors in the given set. C1, C2, C1, C3, C5 means V1, V3, V5 vectors will form basis for H. That is, by the result, by spanning set theorem, the columns which are not pivot columns can be removed because they are linear combination of other columns, and the remaining make basis. So this is what the procedure we are going to use when we come across with the numerical problems of finding a basis for the spanning set. Let us look at a problem which is based on the spanning set theorem. Find a basis for the space spanned by the given vectors. Here you are given 1, 2, 3, 4, 5 vectors, and these 5 vectors, they belong to R4. And now we have to find a basis for the space which is spanned by these vectors. Let us see the solution. So let H is equal to span of vectors. So I'll give these vectors V1, V2, V3, V4 and V5. So H is span of V1, V2, V3, V4 and V5. Now we have to find a basis for H, and this set containing V1, V2, V3, V4, V5 is a spanning set for H. To find a basis for H. So what is the procedure? Before I gave you some procedure, you have to consider a matrix by taking these vectors as columns. Because this is a spanning set given to us, we have to find a basis from this spanning set. So let us take matrix A is equal to. So first column is the first matrix V1, 1, 0, 0, 1. And the second column minus 2, 0, 0, 2. And the third column 3, minus 1, 1, minus 1. Fourth column 5, minus 3, 3, 4. And the fifth column 2, minus 1, 1, 0. Now according to the procedure, this matrix we have to reduce it to echelon form. Reducing A to echelon form. So first let me mark the pivot position. So this first row, first column 1 is pivot position. Using this we have to make all these 3 entries zeros. Already this is 0 and this is 0. The last one I have to make 0. So I will apply for R4. For R4 I will apply R4 minus R1. Then this matrix is transformed to 1, minus 2, 3, 5, 2, 0, 0, minus 1, minus 3, minus 1, and 0, 0, 1, 3, 1, 0, 2, minus of minus 2, which is 4, minus 1, minus 3, minus 4, 4 minus 5 is minus 1, and 0 minus 2 is minus 2. Now again let us mark the pivot position. This is pivot position, and we made these all zeros. Fine. Now the first row pivot position work is over. Second row pivot position, this is minus 1. Using this minus 1 we have to make these two zeros. So we have to change R3, transform R3. So for that what we have to use? R2. So this will be, how can you make it 0? So you can just add R3 plus R2 will give you 0. Then what about R4? I have here minus 4 and I have here minus 1. How can I make it 0? I will just minus 4 into minus 1. That will be 0 for me. So what is my task here? For R4, this is R4 minus 4 times R2. 4 times R2. So this matrix is transformed to 1, minus 2, 3, 5, 2, 0, 0, minus 1, minus 3, minus 1, and then 0, 0, R3 plus R2, R3 I am transforming, 0, R3 plus R2, 0, R3 plus R2, 0, and then R4 minus 4R2, this is already 0, 0 minus 4R2 will be 0, 4 minus 4 times 0 is 4, minus 0 is 4, and then minus 4 minus 4 into minus 4 plus 4, 0, and then minus 1, minus 4 into minus 3 is 12, 12 minus 1 is 11, and then minus 2, minus 4 into minus 1 is plus 4, and then minus 2 plus 4 is 2. Now let us see the pivot positions again. This is pivot position, this is pivot position. Then I have come for the third row. There is no pivot position, this is a 0 row. Then what is our task in echelon form? To send this 0 row to the next to the last row. This we have to do in the next step. Now our aim is to send this 0 row to the last. So for that, what do? I will interchange R3 and R4. So this matrix is reduced to, transform to, you can say, 1 minus 2 3 5 2 0 0 minus 1 minus 3 minus 1, and then 0 4 0 11 2 and 0 0 0 0 0. Now let us mark again the pivot positions. So this is pivot position, and this is pivot position, and the next one is this is pivot position. But here comes the pivot position in the third row should be to the right side of the pivot position of the second row. So how can, this is wrongly placed here, how can we rectify this? We will just interchange these two rows. So for the task now is to interchange R2 to R3. So this matrix is transformed to now 1 minus 2 3 5 2, and then 0 0 0 4 0 4 0 11 2, and then 0 0 minus 1 minus 3 minus 1 0 0 0 0 0. So let us mark again the pivot positions. This is 1, and here the pivot position, and here the pivot position, and these are all zeros. This is all 0, and these are all zeros, and there are that 0 row is sent already to the last row. So now this is in echelon form. Now how are we going to conclude from this that finding a basis for the given space? So here I have, this is C1, C2, the columns C3, C4, C5, where these three are pivot columns and these three are not pivot columns. Then what does it give us? So non-pivot columns, so we have some results like this. Pivot columns C1, C2, C3 form Li, and one more result is C4, C5 non-pivot columns are linear combinations of remaining vectors. That's why they are not pivot columns. Then what is there in the spanning set theorem? Then by spanning set theorem, because this is a spanning set v1, v2, v3, v4, v5, set theorem, c4, c5, that is what are the corresponding vectors, v4, v5 can be removed and still the remaining vectors, what are the remaining vectors which are in the column C1, C2, C3, that is V1, V2, V3 span the given space. So after you remove these vectors which are linear combinations of the remaining vectors, the remaining vectors will be spanning the set. Therefore, we have the set S is equal to V1, V2, V3. This is from A, not from the echelon form. From A, matrix A. What are those set containing? What are those vectors? 1, 0, 0, 1, minus 2, 0, 0, 2, 3, minus 1, 1, minus 1, and then that's it. These three vectors. This is S, and where I can say S is Li, and then H is span of S, because it is already given that H is span of S. Hence, S forms a basis for H. This is what finding a basis from the spanning set using the spanning set theorem. Here are some practice problems on the same model what I explained before. Find a basis for the subspace spanned by the following vectors. So here are 1, 2, 3, 4, 5 vectors given, and these are in R4. And these vectors 1, 2, 3, 4, 5 vectors, they are given in R1, 2, 3, 4, 5, R5. So just check from this. These are spanning sets are given for the subspace. Find out a basis from this. Let V1 is equal to 4 minus 3, 7, V2 is equal to 1, 9 minus 2, and V3 is equal to 7, 11, 6. You are given three vectors such that H, that's a subspace H is equal to span of V1, V2, V3. So H is spanned by these three vectors. That means H can be like all the vectors in H are linear combinations of V1, V2, V3. It is given. Now you have to verify that 4v1 plus 5v2 minus 3v3 is equal to 0. That is first one. And find a basis for H. So because you are given here that H is a span of v1, v2, v3, you learned in the previous examples by spanning set theorem, you can obtain a basis from these three vectors for H. After that, the question is this basis unique? Now let us see the first one here. First we have to check the condition 4v1 plus 5v2 minus 3v3 is equal to 0. So what is 4v1? 4 into, so 4v1 plus 5v2 minus 3v3 is equal to 4 into 4 minus 3 7 plus 5 into 1 9 minus 2 and minus 3 into 7 11 6. So this will be equal to 16 plus 5 minus 21 minus 12 plus 45 minus 33, and then 28 minus 10 minus 18, so which is equal to 0, 0, 0. So this condition that 4v1 plus 5v2 minus 3v3 is equal to 0, this is verified. Now our next concept is to find a basis from these three vectors given which are span of, and we learned earlier that by taking these vectors into a matrix we can check whether which vectors can form a basis. Before that, let us check this equation once. So if this equation means, if I give this equation as equation 1, so 1 implies I can write 4v1 plus 5v2 minus is equal to 3v3. That implies I have here, so I have here v3 is equal to 4 by 3 v1 plus 5 by 3 v2. What do we mean by this? V3 is a linear combination of V1 and V2. So that implies set containing V1, V2, V3 is not Li. So one vector we have to omit. So let us remove V3. Then what is our new set? Set containing V1, V2. Now let us check this whether this can form a basis. So we will check here now to check whether set containing v1, v2 forms a basis. Since we deleted the vector which is a linear combination of some vectors, we'll have H can be still spanned by H can be still spanned by v1, v2. So what do we have to check? So we will check v1, v2 is Li or not. So for that I will take here, let A is equal to, I'll take how to check v1, v2 Li or not. What is v1? Minus 4, 3, 7. And what is v2? 1, 9, minus 2. So let me check whether this, you can take 0, 0, 0 or you need not take, both will be the same. So I have taken 0, 0, 0 and then I'll use the transformations to make find the pivot positions and all. So what is my pivot position here? This is pivot position. Using this, these two I have to make zeros. So I'll use here the operations for R2. So 4 times R2 plus 3 times R1, and for R3 I will make 4 times R3 plus 7 times R1. So this will be transformed to this matrix. A is transformed to, so minus 4, 1, 0, and then this is 0, and 4 times R2, 4 9s, 36, plus 3, 3 ones, 3, 39, and then anyway this is 0, and the last one is, this is 0 because 4 7s 28 plus minus 28, 0, and then this is minus 8 plus 7, minus 8 plus 7 is minus 1, and the last one is 0. So this is, and then here you have pivot columns, pivot positions, sorry. So still I have to make the 0. So what do I do? Then the next step, from here I will apply, this is pivot position, I have to make these zeros. For R3 I will multiply 39 times R3 plus R2. So this matrix will be transformed as minus 4, 1, 0, and then 0, 39, 0, 0, 0, 0. So let us mark pivot positions. This is pivot and this is pivot. So you have, how many variables you have in this? How many vectors? 2 vectors. So 2 variables. So 2 columns, C1, C2. So what do you say here? We'll say that here no free variable, no free variable. So what can we say? If there is no free variable, therefore this forms Li. Therefore we got here that set containing v1, v2 is linearly independent. Hence it forms a basis for H, because it also spans and it forms a basis for H. So we got a basis for H. But still there is something else asked. Is this basis unique? Now how did we get this v1, v2? By writing the first equation in terms of v3. So we can write, so we can also write, equation 1 implies 4v1 minus 3v3 is equal to minus 5v2, which implies I have v2 is equal to minus 4 by 5v1 and then plus 3 by 5v2, which is a linear, not v2, this is v3. It is a linear combination of v1 and v3. Therefore, so what do we have here? Remove v2 by removing v2. Earlier we removed v3, so we get a set v1 v3. And what about this set v1 v3 such that H will be still spanned by v1 v3? Also, we can check v1 v3 is linearly independent. v1 v3 is linearly independent, like how you checked in the previous v1 v2 is alike, the same way you can check it. So therefore I can write here v1 set containing v1 v3 is also a basis for H. And similarly, 1 implies we can write 3v2, 5v2, sorry, this is 5v2 minus 3v3 is equal to 4v1. So that is v1 is a linear combination of 5 by 4v2 minus 3 by 4v1, and proceeding as in the above. So in the same above way, set containing v2, this is v1 is 3 by 4 v3, this is right, v2 and v3, set containing v2 v3, set containing v2 v3 is also a basis for H. So not just one basis here, you have two bases, you can find here two more bases for the same subspace given under the given conditions.